So the first two speakers we have today is Jessica Pointing. Please welcome Jessica.
Hi.
Maybe you want to sit here. And Murray, welcome.
Thank you.
Please sit over here. Okay, so we have been working at the conferences here at GOTO to figure out what's up and down in this world, and for some time now, and this year intensively. And Jessica, you gave a number of talks. You also gave a number of talks in Berlin and other places, and you were also in Chicago. So, but how many of you actually saw one of these two speak before? Yeah, not so many. So I think, Jessica, you're the one who can explain really quickly what this is all about. So could you just give us like a 2-3 minute introduction to quantum computing?
Yeah. So a quantum computer is a fundamentally new type of computer that could help us solve certain types of problems significantly faster. And it does this by using quantum physics, which describes how the world works at the level of atoms and subatomic particles such as electrons. And it harnesses quantum physics to enable us to do faster computation. But it's not just a faster computer overall. We have to specifically figure out what problems can we do faster in a quantum computer. And some people have already found some potential future applications in chemistry, machine learning, in security. And that's why a lot of people are excited about quantum computing and why we're talking today.
Yeah, maybe explain the superposition concept.
Yeah, so I have this donut to explain it, but I don't have it with me here. But basically,
imagine a donut.
Imagine a donut. So you have computers, they process and store information in bits, zeros and ones. So you have 0 and 1, but a quantum computer uses quantum bits instead of just normal bits. And these quantum bits can be in superposition, which means that it can be a combination of 0 and 1. And because of that, that gives you a lot of power, because now you can sort of process on multiple combinations instead of just one combination at a time.
Thank you. You want to add something to that?
No, I think that's a good way of describing it from the perspective of superposition. The main thing is that, if you think about some of the problems you might be working on, like adding numbers together, that's a scenario where you're not necessarily going to want to have superposition, right? 1 + 1 = 2. You don't want it to come up with like a bunch of different values. But if you're working on some types of problems like I have a model for how the world is going to work, and I want to figure out the optimum way of working through it. So like I know how many crews I have for airline scheduling, and I want to figure out how to assign them to the different planes so that my network of plane routing works as effectively as possible. There, you're not quite sure what values the variables should take to get you the optimum answer. And that's the type of thing where superposition can really help you out.
Okay, so Jessica, you recommended me this book, Quantum Computing: An Applied Approach, and this is this has been going on for decades, and you don't know anything about this, you should read this book. And I bought it. It's actually sold out, but it's being printed again, and it's like going back to school. It looks like a school book inside, a lot of formulas and things like this. But on 81. Because there's the other concept we didn't really talk about, it's called entanglement. And on 81 in this book is called teleportation, quantum teleportation. Maybe you can talk a little bit to that.
Okay, yeah. So let's come over to explaining entanglement. I'll just give a little experiment. So let's say you have 2 boxes, and you have, let's say, the bits 1 and 0 in a pink box, and let's say the bits 1 and 0 in a blue box. And now you shuffle it, and I ask you to randomly draw out 1 ball from each box. Well, you would have a 25% probability of getting either combination, so 25% probability of getting 1, 1, or 0, 0, or 1, 0, 1, or 1, 0. Now, if I actually entangle these boxes together, you can end up getting different probabilities. So I could actually get a 50% probability I'll get 1, 1 from these two boxes, and a 50% probability I'll get 0, 0, and a 0% probability I'll get 1, 0, and 0, 1. And if you actually think of it in terms of the experiment of drawing out the boxes, that's crazy, right? Because how is it possible that you'd get 50% of just 1, 1, and 0, 0? And this is entanglement. And the idea is you're now correlating the outcomes are correlated. So I know if I draw out 1 from this box, I know that this one now must be 1. It can't be 0 because there's a 0% probability of having 1, 0. So this is an idea of entanglement, and this is another quantum effect in addition to superposition that you can use for quantum computation. So you can use entanglement in many special ways to do very interesting problems.
And for communication in a very safe way?
Yes, yes. So you could, some people are working on this, but yeah, and the idea is that you could do more secure communication with entanglement, because basically if you have this entanglement property, you can because you can correlate the outcome of the bits, you can actually figure out when there are basically these schemes where you can figure out and make more secure systems. And there's a lot more details into it. But basically, you can make more secure systems by using this entanglement, and that's why you can use it for that.
Okay, but let's talk a little bit about what it can be used for. What can quantum computer technology give us? So let's maybe talk about 5 practical use cases. I know you just gave a talk, and you have a lot of practical use cases. Maybe talk about a case you have with a customer. Maybe, yeah.
Mm-hmm. Yeah, absolutely. So the most practical examples that I've been thinking of here. So we've heard tell of like algorithms like factoring numbers and the quantum supremacy experiments. Many things that we're doing with quantum computers, or that researchers are doing with quantum computers, is sort of exploring what quantum mechanics can do itself. And so I'm kind of looking at it from a slightly different perspective, which is like, how are we going to turn that quantum mechanics into useful work for ourselves? The applications that, like one of the applications I spoke about was Volkswagen is looking at basically taking live data from traffic flow, and rather than optimizing the path for an individual driver, or let's say saying, hey, the path from the city to the airport looks like it's got a lot of traffic, so let's just reroute all the drivers onto this alternate path. The challenge with that is that if everybody takes that alternate path route, then it's also going to get clogged. I've actually had that exact experience with Google Maps. So the notion here is, how do you optimize all of the cars and basically set them so that you select a series of routes for all the traffic patterns, so that the overall traffic is minimized and everyone's sort of average time is improved as much as possible. And that's the path that Volkswagen has gone down and now actually demonstrated at the 2019 Web Summit in Lisbon. Other examples are from completely different spaces. So there's a group, a company that does automobile manufacturing, Denso, in Japan, and they've looked at routing and optimizing how the robots in their manufacturing facilities actually move around one another so that they don't get in each other's way, and actually can bring parts to various areas of the plant in the most efficient pattern. And there's also another company in Japan named Recruit Communication Systems. They've also been working on online web advertising. So that's a scenario where, let's say you're a company, you want to do some advertising online, and so based on what people are looking for and what they're doing in their browsers, you can basically purchase a little advertising window in their browser and say, hey, I'd like my ad to pop up there. And you can get data about like what did they search for, or what were they just looking at, in an anonymized way, I should add, to sort of pick whether or not you think that quantum computing or let's say hotels that you're advertising is going to be relevant to their search history. But in addition to that, the difficulty with choosing your online marketing is making sure that you don't spend all of your money in one place relatively quickly. You're trying to create an algorithm that chooses your advertisements for you. And so they use the quantum computer for budget pacing. So if you see that you're actually choosing a lot of advertising very quickly in the morning, but you actually want to spread your budget out over the whole day, they've actually created an optimization which basically calls the quantum computer that accepts or rejects choices to advertise at a particular point in time, so that you basically pace your advertising over the whole day and spread it out. So just sort of a lot of interesting, challenging problems that some of them sound, every day, like traffic flow, and some of them can be quite unique and sort of tailored to a particular application, where just getting the best result, improving efficiency, coordinating activities can be difficult to do with a classical computer, and making a remote call to a quantum computer can help.
Thank you. Jessica, have you discovered some practical use of quantum computing on your traveling the world tour?
I mean, that would be the next milestone, quantum advantage, which I mentioned. So, I mean, that's what people are working towards now. We demonstrated the quantum supremacy experiment, which, the quantum computer could actually outperform the world's best supercomputer for a very particular task, but people think that task is kind of useless. So now the next goal is to find a useful task where we could run it on the quantum computer and it outperforms the world's best supercomputer. But people think maybe the first few applications of quantum computing would be around quantum chemistry or physics simulations, and basically because that is what a quantum computer does. It is inherently quantum, so you could understand and simulate quantum systems or molecules, atoms more efficiently. And people are working on this at the moment, and maybe, hopefully in the next few years, we'll actually see a practical use case there.
So maybe from the theoretical point of view, you could explain this quantum supremacy a little bit more, because it happened very recently.
Yeah.
And exactly what was the problem that was solved, and how much faster was it solved than it could be done on a supercomputer?
Yeah, so Google did this experiment down in their lab in Santa Barbara, which is in California. And the idea was, so they have this quantum computer with 53 quantum bits, and they ran an experiment on it, and they said it took 200 seconds, and they compared it to the world's best supercomputer, and they claim it would take 10,000 years to solve this problem. Now, you may be like, what is this problem? So the problem is, well, it goes a bit more into theory, but in my talk, I talk about quantum gates. And basically, our computers, we have logic gates, and you can have the equivalent quantum gates. So what they do is they take quantum gates, and they actually just arrange it in some sort of random sequence, and it's called a random quantum circuit. And then what happens is when you have this random quantum circuit, it actually produces this very complex probability distribution. And then at the end, you can sample from this probability distribution. So let's say, 10 times I get this answer, 9 times I get this answer. And then you produce all of these samples. Now, on a supercomputer, it's very difficult to actually sample from this complex probability distribution. And there are actual theoretical proofs for why it's hard to do. So therefore, on the supercomputer, you'd actually have to directly simulate what the random quantum circuit is doing. And I also mentioned in my talk that these quantum gates are basically matrices. So when you're simulating it, you're just multiplying all these matrices together. But that would take, these matrices can get so large, it would be really hard to do on the supercomputer. So on the supercomputer, they basically directly simulate what the quantum circuit is, this random quantum circuit is doing. And it's so hard that it would take up to 10,000 years, they claim, to actually do this problem. So as you can see, a random quantum circuit isn't maybe that useful, but people actually think there might be applications in security. But yeah, so people are working on that.
So there will be some fairness when they point you and they want to test you in the airport. It's really random.
Yes, exactly.
That's good. I look forward to that. I always think it's unfair. It's always you. Okay. So, but let's talk a little bit about the environment and the energy consumption, because I think that's something that is super interesting here. Because you just mentioned it a little bit, Jessica, that it would take longer on a supercomputer. But in your talk earlier, you actually talked about comparing energy consumption from conventional computers to quantum computers. And one of the things you mentioned is that once you're at the chip level of a quantum computer, it's superconducting, meaning that it basically doesn't consume any energy. And maybe just talk this whole through about your visit to a supercomputing lab or computer center at NASA, how that was compared to what you see in everyday life.
Yeah, absolutely. So the thing for us to keep in mind is that the computers that are in our laptops or in our phones, right? There's computer chips in there that are doing calculations for us. Their operating temperatures are room temperature. But when you turn them on, they produce heat and they start warming up. And in fact, if you don't try to cool them, they can actually melt themselves. So you actually have to put a lot of energy in to basically allow them to do their computation, and that they use up that energy and basically turn it into heat dissipation. And then you have to add more energy into it to get that heat away from where the chip is located. And the interesting thing about the quantum processors that we're building at D-Wave, and that most of the major players are working on right now, is that they're built with superconducting metals. Now, as Jessica pointed out, you could choose to build them with a lot of other different quantum materials. The reason why superconductors are particularly popular is because it allows you to fabricate them on integrated circuits. And integrated circuits, also related to Jessica's talk, is the reason why transistors beat out vacuum tubes. You can get much more highly integrated circuits fabricated efficiently than you could if you're actually plugging vacuum tubes into circuit boards. So that's the reason why people have gone to these superconducting metals. And if you're using a chip with superconducting metal, then when you're actually flowing current on the chip, you don't produce any heat whatsoever. It doesn't warm up. And the only time that you do dissipate heat is usually when you read it out or when you erase state. Then you basically say, okay, just flush whatever state my memory is in, and that produces a very tiny amount of heat. The power consumption I mentioned earlier on is a tenth, I should say, this is the total power budget for the chips that we produce, is a tenth of a billionth of a watt. So 0.1 microwatts. And if we produced any more heat than that, what we'd actually notice is the chip itself would start warming up. But by thousandths of a degree, we can actually see the change in results when the processor will actually change by thousandths of a degree. So from our side, from the manufacturers of quantum computers, that's a brutal engineering challenge that we've actually managed to get a lot of control over. And from a user side, you get all the benefit of that in terms of the computational power without the same power consumption. And the significance here are these supercomputers. I was mentioning that the Pleiades supercomputer at NASA, there's also a supercomputer at Oak Ridge National Labs. They can consume megawatts of power. In some cases, tens of megawatts of power. And, the power used to operate them is, over a 3-year period, is as expensive as actually purchasing the computers themselves. So being able to do future compute at, a much lower scale, it's not just that, your baseline power consumption is for the support systems, those pumps and compressors. But then as the processor technology is scaling, you don't get a scaling of energy as the processor develops, which I think will be really powerful.
Thank you. That's really interesting, I think, to follow that. And okay, I just want to ask the audience, how many of you have secrets? I mean, that you, in your company, do you protect your data, or doesn't it matter? I mean, when you send information from A to B. Let me see a raise of hand. How many encrypt data? Oh, why? Okay, so Jessica, you mentioned in your talk this thing about Shor's algorithm, and the cryptography we have today is based on, for instance, RSA. Mm-hmm. Can you talk a little bit to that? What we should expect in the future, maybe in 5 years and 50 years, or when it will happen? What will happen then?
So I mentioned in my talk that, well, actually one of the big reasons quantum computing took off was because this professor called Peter Shor in the 1990s invented this algorithm that could basically break RSA which encrypts a lot of your data, bank information or whatever, on the internet. But when he created this algorithm, he assumed we would have, the ideal quantum computer. It was purely theoretical. And then, over the past few years, we've actually been able to build quantum computers. But the thing is, the quantum computers we built are not at that stage where they could actually run Shor's algorithm for, for a really large number that would actually break your data on the internet. So to give you a perspective, we have around 53 qubits, quantum bits right now. And people estimate to actually break encryption, you would need millions of quantum bits. So it's quite a few years away. But it is something we should be thinking about, which I mentioned in my talk, because we need, to replace all of our encryption systems would take a long time. It could maybe take 10 years, and maybe in 10 years we'll have those quantum computers, who knows? So it's something we should be thinking about, new safe methods to encrypt our data.
Thank you. And also because most people, they communicate over the open internet, so anyone can just copy whatever data they want,
yeah,
and then store it,
yeah,
and maybe in 25 years decrypt it.
Yeah.
So maybe it doesn't matter, because it's not going to intervene in a transaction in a bank, because the money will still be in the right place, because it's happened 25 years ago.
Yeah.
But there might be other secrets that you don't want to get out in 25 years' time. So there's just a little thing. As you said, it is creating a lot of funding in this field.
Mm-hmm.
Yeah?
So, yeah, I was just going to mention a point, because Jessica mentioned about having 53 qubits, but I saw and some of the questions that came from the talk, they were sort of like, wait a second, you said you had 2,048 qubits. So I should mention that, I should probably touch on that point, because some of the questions are like, well, how many qubits have you got, and what's the difference? So in the origins of quantum computing, which were popularized in the 1980s by Richard Feynman, it was this idea of creating quantum computers so that we can solve quantum-related problems. And I think it was in 1994 when Peter Shor published that algorithm about factoring. And there was a framework that a group of theorists came through in terms of how to write algorithms for a quantum computer. And in 1998, a different framework was proposed. It wasn't based off of gates, it was based off of annealing, about constructing a network or an entire problem and then basically annealing it all in one go. So the difference is that it's kind of like how we do computing today. You're trying to solve some big problem. Well, you are actually working through many, many layers of abstraction in your computer, and that's getting broken down into a series of flops, right? You've all heard megaflops of computation and things like that. Each one of those floating point operations, those flops, is basically just an addition or a multiplication step. It's getting broken down into those steps, and it's running billions and billions of those. That's what the idea is with gate model, is that you're producing these very small local gates, and you're doing computations over small amounts of your quantum space. But you have a lot of control over those. And in quantum annealing, it's an equivalent model. You can solve the same types of problems. But instead of basically breaking it down into a series of small steps, you're actually just basically putting the whole problem in at one time and then saying, okay, now just relax to a solution that you're trying to obtain. At D-Wave, we realized that in order to build a machine to do Shor's algorithm, some of those, you know how Jessica was talking about spinning the qubits? Well, you can spin the qubits not just this way, but this way and this way. And in order to be able to control a qubit so you can do any of those requires a degree of engineering control, which we determined was going to be too difficult. We didn't have 20 years to build quantum computers. We're a startup, so we got to do it much faster than that. So we actually let go of Shor's algorithm. We decided, okay, we're not going to factor numbers that way, but we're going to work on network optimization problems and machine learning problems and financial problems. And the interesting thing about that is that you can actually factor numbers with quantum annealers in a different way. And the interesting thing is that I talk to a lot of experts, and they sort of say, well, sometimes I'm worried about encrypting my data right now. Sometimes I'm worried about someone discovering that data in a year. Some people are worried about data getting decrypted within 40 years. And so what they're not sure about is that if you use a quantum annealer or a universal quantum annealer, how fast is that algorithm going to be? They know how fast Shor's algorithm is. And for those people who need to assure that that data is going to be safe for decades in the future, they're starting to look at post-quantum cryptography to help them out.
Thank you. Okay, so if you are a decision maker in an enterprise today, and you have thousands of people or just dozens of people knowing about classical computing, but you hear this for the first time, then you might think, oh, when is the time to get into this, and how much effort is a meaningful effort? So Jessica, maybe you can start answering this.
When is the time to get into quantum computing?
Yeah, and what is the meaning? I mean, you kind of, you're still young, but you spend a lot of your life getting into this.
Yeah.
But I also know from Jack, he has a group at Google, and they have different experiences with how quickly people pick it up, and when is it useful? I mean, when is the time to start looking into this?
Yeah, so I mean, I guess I'm biased to the now, since I'm doing it now. Yeah, I can talk more about, getting to know more of the weeds of it and doing quantum programming. Maybe you can talk more about the business side. But so I think, yeah, you can get into it now. As I said, right now the existing quantum computers exist, and it's really exciting because you can run quantum programs through the cloud, and a lot of people, anyone has access to the quantum hardware. IBM has made it open source in a sense, so you can run anything on the quantum computer. The real question, though, you have to sort of manage your expectations in a sense. As I mentioned, right now we can't do anything practically, at least with the gate-based model quantum computing. I'm talking about practically with, let's say, Google's quantum processor or IBM's quantum processor. So right now, it's more sort of research, I would say, trying to figure out what can we do with these quantum computers. And I think once we've reached that milestone, then I think a lot more people will get into it, right? Because now there's something tangible we can work with, and then more people will start building applications on top of that. So at this point in stage, it is sort of still trying to figure out what can we practically do with quantum computers, and there are a bunch of startups working on this. In fact, there are sort of just these consulting startups that will talk with big companies, and they will have a bunch of quantum researchers, and they'll go to the companies and they'll ask them, what are the hard problems? And they'll try and come up with quantum algorithms to try and solve these hard problems. So that is sort of, people are working on this right now. Yeah, so I think any time is the right time to get into it. I think later on it will be more established, but yeah.
And another good way of looking at it from a business point of view is that you say there are a lot of startups, and in fact there are more than 100 startups who are already doing a lot with quantum computing.
Yeah.
And we now start to see consultancies, they can act as your advisors for when to start and what to use it for.
Yeah.
But you also talked about some things that we do very useful things we can do already today, and with even small investment of time, you can actually get pretty far. Maybe talk a little bit about your program and how you can get into quantum computing from your perspective.
Yeah, I've definitely thought a lot and talked to a lot of people about the challenges of, in like a business context today, of like, how are we going to incorporate a disruptive technology? Because even based on the name of it, we don't really want to actually disrupt our company while we're actually trying to bring in some new technology into the space. So I've definitely spoken to a lot of folks who are facing the decision of, are we going to build in our own internal expertise, or are we going to purchase the ability? So are we going to contract to a professional services organization that has a group that has expertise in quantum computing, or are we going to try to build that in-house? And I think that every sort of business leader has to make that decision for themselves based on the size of their team, the breadth of the company's problems. Lockheed Martin, when they started, they were looking at cyber-physical systems. So they make jet aircraft, and they have a lot of software controlling how those aircraft move. Well, the problem of debugging that software in those jet aircraft, they have some very strict regulations. It costs them $50 million every day to debug their software. So for them, they're thinking like, okay, we've got to be like much further out. We're going to build a consortium of people. We're going to have our own expertise. We're going to find out like what kind of business problems we have that are related to quantum computing. There are folks like Google whose whole basis of their company, everyone thinks about Google as search, but Google is all machine learning, right? Translation, advertisements, searching, all of those things that it's doing, image recognition, are based on machine learning techniques. And the types of things that I was talking about, optimization and networks, those are all related to machine learning. So, we published a couple of papers last year on quantum material simulation, and a Nobel Prize physicist who had done the theory for the type of simulation we had done said this represents a breakthrough in material simulation that is effectively otherwise essentially impossible. So imagine that, super exponential growth curve that Jessica was talking about, where one day you're like, well, these computers are piddly, right? Well, they're growing with a performance curve that's an exponential on top of an exponential. The point at which that crosses, you're going to get to this period like that physicist said, where it's like, well, now this problem, the only way to solve it is with a quantum computer. We would have previously used supercomputers, and now you would never bother even trying. So if your company is based on machine learning, and that's everything that you do, then it's incredibly strategically important for you to know when is the point in time when all of a sudden, the only way to solve these problems is on a quantum computer. But many of us are dealing with things at like a much more granular scale, maybe even at an individual level. And so that's the idea behind hybrid quantum computing and cloud services and educational resources, is to allow people to get started at the pace that's appropriate for them. Maybe you've got a team of 6. Maybe, in your 20% time, you're going to allow some of your team members to actually go online and spend a week, trying to see if they can take one of your company's problems and put it on a quantum computer. And those are all realistic now. You don't have to spend $3 million to get started with a quantum computer. You could basically get started for free. Hopefully that will help people, I think, at all different areas of our economy and in all different businesses find the right time for them.
Thank you. And okay, so later today we actually have a talk about what's going on in China and how we should pay respect to the research happening there. Can you just share what you know about what's going on regarding quantum computer there in China?
Yeah. Well, I think China has invested a lot of money into quantum computing. Was it $11 billion or something? Mm-hmm. So they're really pushing forward, and I think Alibaba has a group on quantum computing, so they're working on that. And I know they've done a few experiments. So we talked about entanglement earlier, and they were actually demonstrated entanglement by using satellites, and they entangled 2 photons across a really large distance. So they actually demonstrated this. So that's pretty exciting. So I think, China's work. A lot of countries in the world are working this, including China, and they have a lot of resources to help push forward this field. So yeah.
Thank you. And I saw this video on YouTube where they explained this China satellite thing experiment with photons. It's pretty amazing. So you should go and check it out. You have some.
Yeah, I think the China is so. Quantum computing is really a worldwide effort. If you go to a lot of research groups in Europe and in North America and in Japan and China and India, we see people. We get requests from Brazil and South America. There are, nations and sometimes unions and sometimes continents which basically come together to form budgets around doing research. But China's really set itself apart because they've really basically put aside the largest budget for investigating quantum technologies totally. $11 billion is an enormous budget. And you can compare that to, let's say, $1 billion for all of Europe or 270 million pounds for the UK. So I think what we're going to see here is that barriers are going to come down. People are going to be publishing results in terms of open research, but you're also going to be seeing people sort of developing sort of proprietary technologies in those areas. And I know that there's universities in Hefei in China that are doing quantum annealing as well as gate model quantum computing, quantum encryption and communications, as well as quantum sensors. So the world is changing quickly, right? The notion of quantum mechanics being this sort of narrow field that's really only relevant to a few physicists is changing. I talk to biologists all the time and chemists all the time who are thinking about how quantum mechanics is relevant to their field of studies. So let's start thinking about it in terms of engineering solutions for the types of problems we're dealing with every day.
Thank you so much. Thank you so much. I hope it was useful to all of you.
Thanks, Thom.